Hi, welcome back to Tennis Backwards. We're now going to look at some of the scientific theories that are applicable to tennis and tennis strokes. We're going to look at three, which at this stage, which are the aerodynamic effect, the bicycle effect, and the coefficient of friction. So let's start with the aerodynamic effect. So we all know that a topspin ball dips, whereas a slice ball flies flat. But why? Well, there's a number of things going on, like differential pressure, but the main one is vectored air. So what's happening is that a ball is grabbing air at the front and then spinning it out at the back. And air has mass, so air that was at the front is now at the back with a velocity. And Newton's law, as you know, says that for every action is an equal and opposite reaction. So if it's the ball's topspin, it's going to grab the air in the nap, it's going to travel around and it's going to spin it out up. So the air goes up, the ball goes down. Now we have to consider gravity. And obviously gravity is always acting in the same direction. So it has quite a different effect on a topspin ball versus a side spin ball versus a slice ball. So start with the topspin ball. So obviously the aerodynamic effect and gravity are acting in the same direction, which is down. So the ball's going to dip more. It's going to strike the court harder, grip more, and bounce higher. Now for a side spin ball, the two effects are acting as right angles to each other. So in effect, they're independent of each other. So the ball's going to travel due to the aerodynamic effect. It's going to travel in an arc, and due to the gravitational effect, it's also going to travel in an arc. Yeah, essentially as if those two things are independent of each other. Now for a slice ball, obviously these two forces are acting in opposite directions, so this becomes a bit more nuanced. So what will happen is that a slice ball initially will fly quite flat as the aerodynamic effect, which is up, and gravity, which is down, they counter each other. But what will happen because of that, the ball will start to lose energy quite quickly, so it'll start to dip, and then it will reach a critical point where it essentially runs out of energy and it stalls and drops to the ground. Now that last point to that bit where it stalls, that's actually quite important, and that will feature later on when we look closely at shots, particularly the slice shots of the slice backhand. The next scientific theory we're going to cover is what I call the bicycle effect. So we all know that a still bicycle falls over, but once you get moving on it, it's stable. And the reason for that is because of the gyroscopic effect of the spinning wheels. Well, the same thing happens with a tennis ball. So a spun tennis ball travels such that it is constrained within its plane of spin. And what is the plane of spin? Well, the plane of spin is the plane that's at right angles to the axis of spin, which we looked at when we looked at the ball. So if I look at that ball like that, which is a topspin ball, I mean it's traveling around an axis like that. So that's the axis of spin. So the plane of spin is at right angles to that. So the ball is traveling so that it's constrained within that plane. But there's something else going on here, and that is that within that plane, the ball has a high variability with respect to its properties. So its properties we're talking about are things like its position, its direction, its speed. Or another way of saying that is that if you hit a ball with spin, and the more spin you hit, the less control you've got over its trajectory. So things like how high it goes over the net or where it lands in the court. If you think about it, that sort of makes sense, because as you hit the ball, like the ball off the racket, you just need to have a slight variation in the angle of the racket, or just slightly mishit it. And as it travels through the air, the combination of spin speed and translational speed can be different, and that all affects the speed and the position of the ball. So that's the bicycle effect. So to summarize, a spun ball travels such that it's constrained within its plane of spin, but within that plane it has a high variability with respect to its properties. Now that may sound a bit obscure at this stage, but trust me, it is important, and that will feature prominently when we start looking at tennis strokes in detail. The third scientific theory we're going to cover is the coefficient of friction. So here's a ball, and I've got to imagine this pot, top of the pot, is the tennis court. So I apply a downwards force on the ball, and I apply a sideways force, and I increase it until it starts to slide. Well, the ratio of the sideways force to the downwards force, that is the coefficient of friction. Now, you might ask, what's this all about? And in real tennis, there's no such thing as a ball sitting on the court with a downwards force and a sideways force. But what we've done here is we've taken a snapshot of the moment the ball bounces. So just before it bounces, it's traveling like that. So it's got a downwards speed, if you like. So it hits the court, presses onto the court as if there is a downwards force. And it's traveling this way as well. So it travels this way. It grips the court and it slows down as if there is a sideways force. So the analogy of the ball on the pot with the downwards and sideways force, that is a valid scientific model. But it gets a lot more interesting than this. I mean, firstly, because there are actually two coefficients of friction, the static and the dynamic. So if we go back to our ball pot model, what I mean by that is that if I apply a downwards force and then a sideways force, I increase it until the ball starts sliding, and then I keep it sliding, I can actually feel it there. The force to keep it sliding is different to the force to start it sliding. So the ratio, that's the force to start it sliding to the downwards force, that's the static coefficient of friction, and the force to keep it sliding, that's the dynamic coefficient of friction. Now in tennis, the dynamic coefficient of friction is different to the static. It's lower. In fact, it's often a lot lower. Now, if you think about it, that sort of makes sense really, because for a start, like the ball's got a nap, so as it starts to slide, that nap's going to flatten and it's going to be easy to slide. And some courts as well, for instance, they have nap types, for instance, like grass or synthetic grass, they've got a nap as well, so that will tend to flatten and make the ball easy to slide. Whereas clay, for instance, like clay has lots of minute particles of clay, so if the ball starts to slide, they will tend to build up in front of it and increase friction. Whereas hard courts, well, hard courts can just vary a lot. I mean, some can be quite slippery, and they'll tend to have quite a low coefficient of friction, especially the dynamic, whereas some maybe not so much. And of course, the other thing to consider is the lines themselves on a tennis court. So the lines will have completely different coefficients of friction. Which brings us to the next point, and that is that the spin on the ball affects ball friction. And the way it does that is it affects both the forces. So in our ball pot model, we've got a downwards force and a sideways force. The spin on the ball changes both of those forces. So if we imagine, firstly, let's look at the downwards force. So there's a ball that you've hit that's flat. So a topspin ball is going to go like that, and a slice ball is going to fly a lot flatter. So you can see a topspin ball, obviously it's traveling down a lot harder, so it's going to hit the court harder and compress more, so the downwards force is higher, whereas the slice ball traveling flat, so the downwards force is quite low. But the spin also affects that sideways force in our ball pot model. So if you think about it, there's a ball that's traveling flat, and the sideways force is proportional to the speed that the ball hits the court. But the speed that's important is the speed at that point there where the ball impacts on the court. So that's a ball that's hit flat without any spin. That's a ball that's hit with top spin. So you can see there the speed at that point where the ball hits the court is the speed that it's traveling that way, less the spin speed, because the ball's going that way, but the spin's going that way. So for a topspin ball, it's the travel speed minus the spin speed, but for a slice ball, it's a travel speed plus the spin speed. So if you think about those two things then, so what we have is for a topspin ball, we have a high downwards force, but a low sideways force, so we're almost certainly in static friction, whereas a slice ball is the opposite. We've got a low downwards force and a high sideways force, so we're much more likely to be in that dynamic friction range. And if we crunch some numbers there, we can look at how it does change topspin versus slice. So for instance, say you've hit a ball at, I don't know, say 80 kilometers an hour and 30 revs per second. So we know that a ball is about 65 millimeters in diameter, and it's a very easy calculation to work out at 30 revs per second, the speed on the ball, the spinning speed at the outer perimeter of the ball is about 30 kilometers an hour. So that means for a topspin ball, it's 80 minus 30, which that's 50 kilometers an hour. Where for a slice ball, it's 80 plus 30, they're 110 kilometers an hour. In other words, the speed at the point of impact for a slice ball more than doubles compared to a topspin ball. So that's the coefficient of friction. So just to go over again, why is the coefficient of friction important? It's important because it affects how the ball bounces. The headline coefficient or the static, it affects, so if you, for instance, if you watch tennis on telly and say you watch the French Open and then you watch Wimbledon a few weeks later, you'll see that both games, the way the game is played on the two surfaces is completely different. And that's because the main reason why that is because the coefficient of friction on clay is much higher than on grass. Now, if we look at the static versus dynamic, that's a little bit more nuanced, and that is that affects how the ball bounces within an individual game. In other words, if a ball bounces to the static coefficient, it will grip and bounce high and slow down a lot. If it's the static coefficient of friction, it will skid. And it's not as if on sort of one court, on one day, one shot, you know, every shot will skid, and maybe a different type of shot, everyone will grip and bounce. It's a lot more subtle than that. I mean, some shots will skid, and then you might do the same shot and it might grip. Some shots might even start to skid and then grip. In fact, some maybe even the other way around. But the point is here, we've now got the tools to know why this happens, skidding versus bouncing, which influences the way your opponent can play the ball. We know how this happens, so what we can do now is we can take that and we can develop tennis strokes to take advantage of this.